Hi, my name is Steven Jackson, and I had a question recently. How do solar eclipses work? Now, I looked into this a little bit with a little bit of research, looking up things on the internet, taking local astronomy classes in my high school and whatnot. I came to the conclusion that I didn't know the sun is the closest star to this Earth. The sun is, I believe, 93 million miles away. That is the closest star. Other stars out there are relatively bigger than our sun. So imagine how much smaller they are than our sun. They're tiny in comparison. Our sun's the size of a fist. They are the size of a fingernail. Now, if you look at this sun, you think, man, that's pretty enormous. How small are we compared to it? Well, you take something like a basketball, an ordinary basketball, and you compare that to something like a lemon. Now, this is much farther away than it appears here. In fact, we'll just toss that because it's so far away. But you take this lemon, and the way an eclipse works is this is the Earth, and this peanut, this small peanut right here, this is the moon. The sun is over there. And if you take this peanut and you hold it to a certain extent, close enough to this lemon, it projects a shadow. And that shadow dwells down to a certain point. And that one point is where the solar eclipse is viewable. Let's go check it out on paper. You have something big like the sun. The sun's huge. Compared to our Earth and our moon, the sun is massive. Now the sun projects light and heat. And that light reaches 93 million miles to the Earth and the Earth's moon. Now the sun, with its light, gives the moon a light side and a dark side. And if you were to look from the Earth at the moon during a solar eclipse, it would be projecting a shadow on the Earth, no matter where on the light side of the Earth you are. Now say if you were up at the North Pole and you looked at the moon, it would be covering part of the sun because of the angle. Now the place outside, the shadow outside of the solar eclipse, is called the penumbra, which is kind of a partial solar eclipse. Now inside is the umbra, and if you were to look from the point of the umbra on the Earth directly out at the moon, it would appear completely covered in shadow. There would be no sun. There are 4 types of solar eclipses. There's a total solar eclipse, a partial solar eclipse, an annular solar eclipse, and a hybrid solar eclipse. Now, total solar eclipse is what we think of when we think of an eclipse. It's blocking out completely. The moon's directly in front of the sun. There's no light getting through, and it's casting the umbra specifically on one spot on the Earth. And we'll say that's on the equator somewhere. Now, a partial solar eclipse would be where the penumbra is. So say if the umbra is on the equator and you're standing in North Dakota, you look at the sun, it's going to be in a crescent shape. Now, depending on where you're standing latitude-wise, that crescent shape could vary. But the moon's blocking only part of the sun. Now, an annular solar eclipse is probably the coolest out of all of them. The sun and moon are aligned so directly that the moon's only blocking out part of the sun, but it's blocking out majority of the sun. There's still a small ring of light around the moon where the sun's getting through. It's like looking into an eye. The last kind is a hybrid solar eclipse. And a hybrid solar eclipse is very rare. It's when an annular solar eclipse turns into a total solar eclipse. Come outside, set up a little diagram of what I thought a solar eclipse would look like. It's pretty elaborate. It's a couple of basketballs. The sun is about southeast right now, which means the shadows are facing northwest. So we're going to take this basketball and we're going to see if we can cast some shadows on a bigger basketball. This is a child's basketball. It's kind of smaller than a normal basketball. You can see it's got a light side and a dark side. The dark side's smaller because it's sitting on the ground. But look how long the shadow is. And if we take the smaller basketball, we hold it over the bigger basketball, look how long that shadow is. It covers a lot more than the normal basketball would. Now, if you hold it in a direct line from the sun to the bigger basketball, you get something like that. And the problem with this is the closer and further away you get, it doesn't change sizes. It just remains the same. We're going to stick with this model right here. We're going to say that that center line right there in the middle is the equator of the Earth. Now, we're going to take our smaller basketball and we're going to cast a shadow right on that equator. Now this is where the umbra would be. Now all around the light side that I showed you earlier of the basketball, that is where the penumbra would be. But the umbra is at one specific spot. There are 2 solar eclipses every year. The good news is that scientists have figured out a way to pinpoint exactly when and where these solar eclipses are going to happen. But the bad news is they don't happen in the same spot for over 100 years. So say if you live in Winnipeg, Manitoba, you haven't seen a solar eclipse since 1979, and your next one's not going to happen until 3356, almost 1,400 years. That's a lot. So let's stick with Winnipeg, Canada for now. The coordinates of this city are about 50 degrees north, about 97 degrees west. But let's focus on that latitude, 50 degrees north, for a minute. In space, the equatorial coordinate system tells us that 50 degrees north up there is simply just stars. The ecliptic, which is the apparent path of the sun, is the celestial equivalent to 0 degrees latitude, or our equator. Since the Earth is tilted 23.5 degrees, the celestial equator itself, not the ecliptic, is also tilted 23.5 degrees. But you have to remember, the Earth is rotating, causing the path of the eclipse to turn and barely miss this city. Now, let's move a little southeast to Montreal, Canada, where they have an eclipse every 91 years. It's a lot more than 1,500. The exact coordinates for this city are about 45 degrees north and about 73 degrees west. That's a little 5 degrees south of Winnipeg. Since the Earth is tilted at 23.5 degrees latitude, that makes the ecliptic's maximum range for hitting the Earth about 23.5 degrees latitude north and south. Now you may be saying, how come I see the sun overhead if it only reaches 23.5 degrees? This dude's an idiot. Well, that's because from the horizon of the Earth, the sun can reach all the way up to 90 degrees, but that is using the altitude azimuth system. But we're using the equatorial system. That system is used for pinpointing celestial objects from the Earth using the horizon and the zenith. But the equatorial coordinate system is more used for giving celestial objects relation to each other, not viewing them from the Earth. Now, hold on to that memory of the latitude of Montreal. That's 45 degrees north. Now let's go back to Winnipeg for just a minute with a latitude of 50 degrees north, 5 degrees north of Montreal. You have to realize that not only is the Earth tilted, it's also rotating. Despite popular 13th century beliefs, the Earth is not the center of the universe, and it is, in fact, revolving around the sun, which we call orbiting. Now, obviously, this has to cause the sun to hit different parts of the Earth at different times. I mean, it has to go away at some point. If it didn't, every day would not have a night, and we'd all look like David Hasselhoff. Now let's talk about the moon for a minute. The moon's orbiting range around the Earth is roughly 28.5 degrees, orbiting us much faster than we orbit the sun at 27 days rather than 365 days. But that's only 5 degrees more than the sun's ecliptic. Now since they're both going around at the same time, you'd think they'd line up at some point, right? Well, remember how I said that there are 2 solar eclipses every year? I was not lying. The 2 masses line up facing the Earth at what we call the nodes. There's an ascending node and a descending node. And whenever the sun and the moon line up at these 2 nodes, an eclipse happens. But just because there's an eclipse doesn't mean that the Earth stops rotating. I mean, it never stops rotating. This causes the umbra of the eclipse to move in sort of a curve motion. This curve, however, is so distinct that it can make even a 5-degree difference of where the umbra hits, giving Montreal more eclipses than Winnipeg, even when they're a mere 5 degrees apart. Solar eclipses are awesome, but you have to remember there's a lot of math and there's a lot of science behind how you pinpoint exactly when and where these things are going to happen. And if you happen to get lucky enough to see a solar eclipse, even a partial solar eclipse, just remember, don't look at it because you're probably going to hurt your eyes. I'm Steven Jackson. I hope you learned something.